As I stated before, in this course, we will make many assumptions and use much simpler mathematical models instead of pursuing the exact solution. In fact, in practice, most engineering designs only require a reasonable level of accuracy instead of the exact accuracy. This is because engineers always design their structures or machines to be stronger and safer than what's determined through calculation, in order to provide protection against any unexpected situations that cannot be accounted for in advance. And this buffer zone in design is characterized by factor of safety. In this class, factor of safety is specifically defined for a load-sustaining member to be the failure load divided by the allowable load. Failure load obviously means that when subjected to this amount of load, the member will fail. It might bend, twist, crack, or break any situation that makes this member unsafe to carry out the function it was designed for. Therefore, the designed load for this member, the allowable load, should be notably smaller than the failure load, and the ratio, the factor of safety, is always greater than 1. Generally, the failure load is determined through experiments, and the factor of safety is chosen based on experience depending on what the actual application is. For example, say if you plan to build a tool shack versus if you plan to build a tree house for young children, I would assume you want to choose a higher factor of safety, in other words, a more conservative, safer plan for the tree house project. But of course, you don't want to choose just a very high factor of safety either, because you also need to tend to your budget to avoid unnecessary waste in resources and money. If stress developed in the member is proportional to the load, don't forget this is an idealization, then the factor of safety can be rewritten as failure stress over the allowable stress. Keep in mind that materials could have different failure normal stress and shear stress, or sometimes even different normal tensile stress and normal compressive stress. Now, with this knowledge as a guideline, we can do some very simple structural design calculations. I will explain that using 2 examples. For this simple truss structure subject to the 2 kilopounds load to the left, all the truss members are made of the same material and have the same cross-sectional area. The failure tensile and compressive stresses are given respectively, and we are instructed to choose a factor of safety of 1.6, and we are asked to determine what cross-sectional area is required for each truss member. So first, let's work out a strategy. If we know the cross-sectional area of each truss member, and if we also know the force in each truss member, then we can calculate the maximum normal stress the truss member is subjected to. And we want to make sure that this maximum stress does not exceed the allowable stress, which equals to the failure stress divided by the factor of safety. Therefore, it looks like in order to find the area, the key here is to find out the maximum load, both tensile and compressive, in the truss members. We learned how to solve for the truss loadings in the course of statics, so I'm not going to repeat the process here. Once again, if you are not sure how to do that, you need to first review statics before moving on with this course. Anyway, the results are here. Letter T stands for the tensile loading, and letter C stands for the compressive loading. Since all the truss members have the same cross-sectional area, the larger the loading is, the larger the stress is. So here are the maximum tensile and compressive loadings. These two will control the area. But we don't know at this point which one of these two will control. Therefore, we will calculate for both situations and compare the results before drawing conclusion. Situation 1. If the maximum tensile force controls, then the allowable tensile stress controls, which equals to the failure tensile stress divided by the factor of safety, which is 16 over 1.6, and that's 10 KSI, kilopounds per square inch. And that equals to force over cross-sectional area A1, which is 2 kilopounds per area A1, and that gives us A1 of 0.2 square inch. And similarly, for the second situation, if maximum compressive force controls, we need to calculate the allowable compressive stress from the failure compressive stress to be 10 divided by 1.6, and that equals to 6.25 kSI. Then this equals to force over cross-sectional area A2, and then we can calculate A2 to be 0.2256 square inch. And if we compare this result to the previous situation, when the cross-sectional area is calculated to be 0.2 square inch, we know that for safety reason, we should choose this larger area. Therefore, the final answer for this problem is 0.2256 square inch for the cross-sectional area for the truss member. Let's look at another example. For this simply supported beam structure, if the pin at point B is subjected to double shear and the allowable shear stress for the material of the pin is given, we need to determine the minimum required diameter of the pin. For this example, since allowable shear stress is already given, we don't need to try to find it through the factor of safety. We just need to make sure that the shear stress experienced at pin B doesn't exceed this allowable value. So the strategy here is to equate the allowable shear stress tau to be the maximum shear force at pin B divided by its cross-sectional area, which equals to pi times half of d squared. And then we can solve the diameter d from this equation. Now the question is, what is the maximum shear force at pin B? Inevitably, we need to start with the force analysis of this beam to determine what is the support force at pin B. Again, we learned how to do that in the statics class. Notice that at point B, there are two force components, a vertical force of 433 newtons and a horizontal force of 500 newtons. And through vector addition, we know that the resultant force here is 660 newtons. This shows that at point B, the force exerted by the support to the beam is 660 newtons. If we zoom in on the pin support at point B in both front view and side view, and the pin is subjected to double shear, this means that the support bracket has two supporting leaves as shown in the side view. And the support bracket and the beam are connected by the pin with nut in this way. Remember, the support exerts a force of 660 newtons to the beam, which means that by action and reaction, the beam also exerts the same amount of force onto the support bracket. But the beam and the support bracket are only in contact through the pin. So these forces actually all act on the pin. From symmetry, we can easily tell that the force acting on each supporting leaf is half of 660 newtons, to be 330 newtons. So let's draw the free body diagram of the pin and use method of sections to determine the maximum internal shear force in the pin. And through equilibrium, we can determine that the maximum internal shear force in the pin is also 330 newtons. Therefore, the average shear stress in the pin is Vmax over cross-sectional area. The area is pi times half of d squared, and that must not exceed the allowable shear stress 10 megapascal. And from there, we can solve that the diameter of the pin must be no less than 6.48 millimeter, and that is the minimum required diameter, the answer to this problem. But just quickly, let's think of this. What if the pin is not subjected to double shear, but single shear? That would mean the support bracket only has one supporting leaf, as shown in the side view of the support. Therefore, through analysis, we see that the maximum internal shear force now is 660 newtons, and if we carry out the calculation, we get that the minimum required diameter is 9.17 millimeter, which is more than 40% larger than the previous pin diameter. So ask yourself, would you choose double shear or single shear in your design? Now please answer the following questions.